Hello everyone. Today we are going to talk about chapter 13, Comets and Asteroids. This beautiful cover image is from a comet Hale-Bopp, which was observable in 1997. You can see clearly it has the iron tail and the bright white, which is the dust tail. First of all, let's talk about asteroids. In the solar system, we actually include many objects that are much smaller than the planets and their large moons. And the asteroids basically all revolve around the sun in the same direction as the planets, and most of their orbits lie near the plane in which an Earth and other planets circle around the sun. And they are actually just small and rocky objects in the solar system. Many of them are the remnants of ancient collision and fragmentation. That means they are already in the current format for billions of years. Asteroids usually giving a number, sometimes a name, because we actually have a lot of asteroids. So you can imagine we'll run out of name quickly. And the Sirius is the largest asteroid, although most recently Sirius is actually reclassified as a dwarf planet. Of course, because its larger size, Sirius is the first asteroid discovered. So therefore, Sirius claimed the number 1 as its alternative name. We'll take a look at Sirius in more detail in next slides. Most of them are in the asteroid belt between Mars and Jupiter. So you can see this image showing the space between Mars and Jupiter. You can see there's a lot of asteroids. Although one problem of the image is that if you draw everything to a scale, the asteroid will be very, very, very small dots, not visible at all. So therefore, the asteroid in the asteroid belt won't be that crowded show as this image. In terms of type of asteroid, there are primarily 3 types of asteroid. Most of them are C-type, which is carbonaceous. So that means they are rich in carbon element. And other than C-type, the dominating the inner belt are what we call the S-type asteroid, which is primarily made from stony material like silicon material. And very few of them are M-type asteroid, which are made from metallic material like iron. If you look at their location of 3 different types of asteroid located, you can see that the x-axis is distant from the sun. You can see the S-type stony asteroid is actually closer, and we C-type, which is the most asteroid, a little bit further away. And among those 3 types of asteroid, we believe the S and the C-type, they are primitive. The primitive bodies or primitive just means those that have changed very little chemically since the beginning of the solar system. We believe the S-type asteroid may form at a different location in the beginning of the solar system from the C-type asteroid that actually made them both primitive but have a different chemical composition. However, the M-type, the metallic asteroid, it's totally different. And it's also the formation we suspect is very interesting. And we believe the M-type consists of cores of differentiated parent bodies. What that means? So basically we suspect that it's a parent body of M-type asteroids. They are large enough, so its interior is molten, So therefore, the material inside will settle out, or what we call differentiated. That means the heavier metal sink all the way to the center, with the rest, the near the surface is a rocky material, which pretty much similar as Earth or other large moons. However, later on, the parent body shattered in a later collision. And after the collision, we believe that the mantle, the rocky material outside the metal core, was just breaking to pieces and therefore flies away from the parent body, only left the metal core actually exposed. And later on, because the size of metal core is pretty small, so they will later on be identified as metallic type asteroid. Actually, the metallic type or M-type asteroid have a lot of metal. It is estimated that there are going to be enough metal in even a 1 kilometer M-type asteroid to supply the world with iron and many other industrial metals for the foreseeable future. However, we need to figure out a way to bring one of them safely to the Earth. Next, let's talk about the mission to the asteroid, as well as let's take a look at some of the examples of asteroid, see how big they are, what their surface feature looks like. And so far, the spacecraft are actually able to image of several asteroids close by, and we're able to return samples from 3 of those asteroids. The first asteroid sample return mission is happening in 2003. It's Japan's Hayabusa 1 mission. It actually visited a very small asteroid called Itokawa, which is the stony type S-type asteroid, which their diameter just less than a little bit over half kilometer across. And you can see from the appearance of this asteroid, this is actually, there's a lot of boulder on top of it. And its interesting shape indicate that might be formed from the collision of 2 asteroids and later on joined together to form this asteroid. And later on, Japan's Hayabusa 2 mission actually visited another asteroid called Yungu, which is C-type asteroid. Is actually collecting a small sample and successfully returned to the Earth in December 2020. They actually found a very rich complements of organic molecule for this mission. And the U.S. mission to return sample from asteroids is we call Osiris-Rex. And they actually visit, again, a very small asteroid called Bennu, which is again C-type and only around like half a kilometers or about 500 meters across. And this mission also successfully bring the sample from Bennu to the Earth for the further analysis most recently. If you want to know more about this mission, you can definitely visit NASA website. You can see this mission sample actually just delivered in September 24, 2023. Now let's watch a video about this mission.
OSIRIS-REx is NASA's first asteroid sample return mission. It launched in September 2016 on a journey to explore a near-Earth asteroid called Bennu. After arriving in 2018, OSIRIS-REx spent nearly 2 years orbiting Bennu, mapping and studying its rugged terrain before carrying out its primary science objective. On October 20th, 2020, the spacecraft ventured to a small crater in the asteroid's northern hemisphere. It dodged jagged rocks and towering boulders and plunged its arm into the loose surface, excavating 6 tons of debris while collecting about 250 grams of material. OSIRIS-REx stowed its bounty and closed its sample return capsule. It bid farewell to Bennu in May 2021, embarking on a 1.2 billion-mile cruise back to Earth. Now, 2 years and 4 months after leaving Bennu, OSIRIS-REx is closing in on the place where its journey began. On September 24th, the spacecraft will approach to nearly 63,000 miles from Earth. It will power up and release its sample return capsule at 4:42 a.m. Mountain Time. The capsule must be jettisoned within a narrow time frame and at just the right angle to hit its target, an area of roughly 250 square miles in Utah's West Desert. Once the capsule is away, OSIRIS-REx will fire its thrusters to avoid colliding with Earth. At 8:42 a.m., the capsule will streak into the atmosphere at a blistering 27,000 miles per hour. It will race across the western U.S. and begin to glow with heat, allowing infrared trackers on the ground to chart its progress. As it pushes deeper into the atmosphere, the capsule will rapidly decelerate, subjecting the Bennu samples to a punishing 32 Gs. About 2 minutes after entry, it will slow to Mach 1.4 and deploy its drogue parachute, stabilizing its descent. The capsule will enter special use airspace at 8:46 a.m., almost 10 miles above the Department of Defense Utah Test and Training Range. Radar stations will lock on and track it to within 30 feet of its landing site. At 8:50 a.m., the capsule will extract and deploy its main parachute 1 mile above the ground. It will make its final descent at a leisurely 11 miles per hour, like a marathon runner savoring a victory lap, before touching down in the desert soil at 8:55. After ground teams retrieve the capsule, the Bennu samples will be taken to NASA's Johnson Space Center in Houston, Texas. The sample canister will be opened in the Astro Materials Acquisition and Curation Facility, and the samples will be curated, distributed, and studied for decades to come.
And if you look at the most recent story, the latest story about this mission, they actually found the Bennu sample actually contains a lot of carbon and water. There's the most recent mission by NASA, which is called Psyche mission. Psyche mission is a journey to a unique metal-rich asteroid orbiting around the Sun between Mars and Jupiter. And if you want to know more about it, you can definitely visit the NASA JPL webpage for Psyche mission. Psyche mission was actually just launched in October 13, 2023. And let's enjoy a short video about the Psyche mission.
There aren't many classes of objects left in our solar system that we haven't looked at up close with a spacecraft. And one of them that's left is the metal asteroids.
16 Psyche is an asteroid that orbits the Sun out between Mars and Jupiter.
The reason that Psyche is unique is that it is metal-rich.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
This is the part of planets that we can't sample directly today.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. So how do we study the core of our planet?
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
After launch, we cruise through interplanetary space for a number of years. First, we fly by Mars for gravity assist that'll slingshot us into the asteroid belt. And then we're thrusting all the way from there to finally arriving at Psyche.
We'll go into 4 orbits to collect the necessary measurements that we need from our 3 primary instruments.
So our payload consists of a couple of imagers, which are cameras that take pictures of Psyche. Also a gamma-ray neutron spectrometer, which allows us to measure the elemental composition of the surface of Psyche. And then a magnetometer, which will allow us to detect any magnetic field that's left at Psyche.
If Psyche still has some sort of remnant magnetic field, that probably tells us it really was a core. It's a strong indicator. We also use the radio on the spacecraft as an instrument, so we can map out the gravity and map out the interior structure that way.
Other than that, actually recent observations have detected there's a number of asteroid moons. For example, if you look at these two, Phobos and Deimos, these are actually the only two moons of Mars. But if you look at their appearance and their size, they are too small compared to the other big, like spherical shaped moons. And if you look at, they look more like asteroid than the regular moon. And we all believe that they might be just two asteroids in the asteroid belt and captured by Mars gravity, then later on orbiting around the Mars, and therefore become the moons of Mars. You can see they are just like the larger one, Phobos, is 27 kilometers across, and Deimos, which is 15 kilometers across. Both are C-type in terms of type of asteroid. And if you remember from previous chapter, when we look at the moon of Jupiter and Saturn, there's a lot of small moons. When you look at their appearance, there are no differences compared to a typical asteroid. And a lot of them, especially the moon of Jupiter, I believe that asteroid in the asteroid belt captured by Jupiter's strong gravity, so therefore later on orbit around Jupiter. Among all of the asteroids, two very large asteroid, Ceres and Vesta, have been extensively studied by the Dawn spacecraft. If you remember, we mentioned the Ceres, which is the largest one, which is also the one asteroid discovered first. Now you may heard about Ceres because its large size. It may be reclassified as a dwarf planet. So it has a number one. And asteroid Vesta is actually have a different kind of surface material. They're mostly made from basalt. And this is number 4. It's also very large. It's like about 500 kilometers if you compare to the rest of much smaller asteroid. And if you look at the appearance of these two large asteroids, you can see definitely clearly one of the most dominant feature is impact cratering, right? As well as Ceres compared to Vesta. So if you still remember, a lot of crater just means the surface is very old. It does not really undergo a lot of surface activity. For Vesta, you can see very clearly at the bottom of the image, this is actually a mountain on the Vesta, even higher than Everest mountain on the surface of the Earth. And you can see as the asteroid become larger and larger, its shape become a little bit regular because it's a larger force of gravity. However, Vesta, you can see, is not spherical, it's not round. If we look at Ceres, and some of its surface image is showing in those two pictures. Again, it has a lot of crater, but on the surface, there is a lot of white material show up on the surface. Actually, at the center of very large crater on Ceres. And we believe that the white spots appear to be the salt deposit. You can imagine it might be like the salty water after it's dried up, only left the salt, the white salt. And if you look at the other image of the surface feature of a Ceres, especially this mountain on the Ceres, which is, we believe, is 4 kilometers high. The reason for this mountain to be up here, we believe, it's due to an intrusion of ice actually underneath the surface. So the ice actually like push up the crust, actually make up the mountain. If you want to look at the more image of these two asteroids, Vista and Ceres. You can definitely visit a NASA website about the Dawn mission. This mission actually extended studied two very different asteroids, Vista and Ceres. You can see they also have a lot of updated story about what is a new discovery by this mission. You can see this one is actually talking about the bright area on Ceres actually come from the salty water below. So that means underneath the surface, the existence of salty water. If you look at asteroids compared to planets, most of them are not differentiated body. You can see none of them, at least from this image, has atmosphere. So the surface is pretty simple compared to the other objects such as planets or the big moons in the solar system. And why we're so interested to learn about asteroids, one of the reasons is a lot of asteroids, they are we call it primitive, that they actually have some secret clue about the formation and evolution of the solar system. And the other reason we're interested in asteroids is because they are small, they orbit around the sun. Some of their orbits are not very stable. Actually, if we look at the history of the Earth, we did have a big asteroid actually collide on the surface of Earth. If you still remember that in the chapter when we talk about the Earth, how the Earth's surface shaped by asteroids, there is a big impact happening 65 million years ago that wiped out the dinosaur. It is actually from a big asteroid, which is 12 kilometer wide. Definitely for the human being, we don't want the similar things happen again, because the one big asteroid collision will basically again able to wipe out all the human civilization. And for all the asteroids that's close to the Earth and may potentially heading towards the Earth, and we give it's a group name we call Near Earth Asteroid, NEA, or Near Earth Objects, NEOs in general. We are especially interested in those objects because of their potential to hit Earth. And one example of the near-Earth asteroid is Potatis. This is actually a small one, 5-kilometer asteroid. Although the size is not very large, but if it hits the surface of Earth, it's of course will actually result a big disaster. Even during the recent history of the Earth, we did have some asteroid impact. A very large one actually happened in 1908. It's actually an asteroid with a size of 16 meters in diameter. This collision took place in Russia in 1908. The place is called Tunguska River in Siberia. Fortunately, because it's not a populated area, so no one get hurt. But you can see that the picture showed that a large area of forest actually destroyed by that impact. The more recent impact is in 2013. There's a small asteroid about 20 meters in diameter actually hit a city in South Russia. And by that time, we actually have a lot of video footage of this asteroid. Let's take a look at the news in 2013 about that asteroid impact.
The images look like something out of a movie. A tiny asteroid tearing through space at a speed of 33,000 miles per hour before streaking across southern Russia. Cameras caught sight of the white trail as it headed across the sky. And then this. An explosion of light, then a massive sonic boom. Strong enough to shatter windows and damage buildings. There were reports of more than 1,000 people injured, mostly from glass and debris. This video shows a children's judo class. Windows blew out here and in buildings around the region. Some people said they thought it might have been a plane crash. This is the aftermath of the blast in a high school. A 17-year-old student put this video on YouTube, showing the reaction in his physics class. Students screamed and ran into the hallways. He said some in the class thought war had started. Some of the incredible images were caught on cameras placed inside Russian cars. Many drivers now record their journeys in case of crashes or run-ins with police. Shock and gasps at the blinding light, the boom, and all the shattered glass.
Asteroid. Реально.
Jim Bolden, CNN, London.
You can see these asteroids actually not really climb directly on the surface. Instead, it's actually exploded about 13 kilometers high above the surface. So therefore, no one get killed, but a lot of people get injured because this big explosion, later on, the shock wave able to reach the surface. Therefore, it's able to blow out a lot of windows. And remember, this is just an asteroid about 20 meters. We actually have asteroid like in kilometers, and we have asteroid in like tens of kilometers. You can definitely imagine if the asteroids over 1 kilometer, the damage it will bring to us if it hit the Earth or just explode near the surface of Earth, it will be a catastrophe. Unlike the planets and the moons, asteroids, due to their smaller size, and most of them actually between the orbit of Mars and Jupiter, they actually have very unstable orbit. And so that means they can just, occasionally they will go off their original orbit and head towards a different direction. So therefore, it makes us to predict the behavior of the asteroid a little bit harder. So especially these near-Earth asteroids. And we believe on the time scale of 100 million years, the fate of most of asteroids will either impact one of the planets as they kind of wandering in the space in the solar system and captured by the gravity of one planet, or they will impact the sun and just kind of evaporates by the solar heat, or they will be ejected in outer solar system. And we believe most of these near-Earth asteroids, they actually come from the asteroid belt between Mars and Jupiter. And some of may be the comets that are approaching the inner solar system, and they run out of their ice, like a volatile material. They become a piece of rock similar as an asteroid. Of course, for us, we're not going to just sit and hope that no asteroid or no big asteroid will hit on Earth in future. Instead, we all actively make plans to defend our planet. Of course, the first step is detect how many near-Earth asteroids actually exist. So therefore, we can keep tracking of their movement and orbit, and then give us alert if there any of them, especially the big ones, is on the path to collide with Earth. And you can imagine the larger the asteroid or NEA near-Earth asteroid will be easier to discover due to their size. And we believe we already discovered over 90% that larger than 1 kilometer. And luckily, fortunately, none of them, the big ones, the ones over 1 kilometer, are on a collision course with the Earth. And of course, we also look at all of them. We look at even smaller asteroid, because even smaller asteroid can result a big disaster on the surface of Earth. The survey is to continue to find the next Earth impactor. And you can see this is the most recent graph, show how many of them near Earth asteroid discovered. You can see most of them are very, very small ones. There's over 13,000 asteroids actually near Earth being discovered. We're especially worried about the large ones, but fortunately we almost discover all of them. So the red one represents the 1 kilometer plus ones. So the size of near Earth asteroid that's greater than 1 kilometer across. And this is not a lot. And the yellow or orange part is actually the asteroid 140 meter across or more, but less than 1 kilometers across. They actually have 10,000 of them, so it's also a lot, right? And how we're so confident we already found 19% of near-Earth asteroid larger than 1 kilometer, is we can see how often the survey, the observation, rediscovered a previously known asteroid. If almost all the asteroid we see are previously discovered, we know we already have most of them on file. The discovery of near-Earth asteroid or near-Earth object are actually performed by this NEO observation programs. So you can definitely go to the NASA website. You can see it called Planetary Defense, NEEO. And in order for us to find those asteroids, the ground-based telescope as well as the space-based telescope, they are actively involved in finding those asteroids. Also, there's a mission called DART, we'll talk about in more detail later. It's how, if we found some asteroid is actually close to Earth, how we're able to change its direction, so let them no longer heading towards the Earth or in future collide with us. And another website I want to introduce to you is the website called Center for Near-Earth Object Studies. You can see there's a latest news about asteroid. If there's any like small asteroid or predict small asteroid will impact with the Earth, so you can definitely read about the news stories. And if you look at the discovery statistics, you actually found the image I show on the slides. As well, you can click by size. You can see what is the percentage of them by size, as well as by mission, by survey. So you can see those are a lot of like a surveying is ongoing from the scientist society. So you can see which mission actually found how many, roughly how many this type of object within a year. And if you return to the cumulative totals, you can see there even a table give you like a daily updates of the newly discovered near-Earth object. Next, as we found all this near-Earth asteroid and keep our eyes on those to see how they move. What happens if we found that one that will move towards the Earth? And of course, instead of waiting for this to happen, scientists actually are actively working on the possible technology for planetary defense. The most straightforward way you can think about to deflect the asteroid that's heading towards the Earth would be to crash a spacecraft in it. So it can either slow it down or speeding it up, and as well as slightly change its orbit. If we can discover the Earth-heading asteroid early, for example, several years, and we employ this deflection effort to let spacecraft crash on it, the asteroid will probably most likely miss the planet, the Earth. The asteroid would miss the Earth entirely. So this means we can avoid the big impact. Of course, alternatively, we can explode a nuclear bomb near the asteroid. So the shock wave basically will push on the asteroid to it deflect away from the path to Earth. The most recent experiment about this technology, this space mission to test the deflection technology, is called DART. We call it Double Asteroid Redirection Test. The idea of DART is it will crash a 500-kilogram spacecraft on a small asteroid called Dimorphos. And the Dimorphos is actually an asteroid moon orbiting around another, a little bit larger asteroid called Didymos. And after we crash the spacecraft on it, we'll use telescope, either ground-based or space-based telescope, and to look at the orbit of Dimorphos, compare its new orbit with orbit before the crash to see if we're able to change the orbit of the asteroid that impact. You can see the DART mission is also very recent. If you want to read more about DART mission, you can definitely go to NASA website about DART and read more about it. And I want to share with you a video about DART mission.
Earth is surrounded by asteroids. Most of them are no threat to us, but some are potentially hazardous. In 2021, NASA and the Johns Hopkins Applied Physics Laboratory launched the Double Asteroid Redirection Test with the goal of smashing a spacecraft into an asteroid to change its orbit.
The purpose of DART is to demonstrate that we can protect the Earth from impacts from natural objects.
Imagine we discover an asteroid that is coming towards Earth.
Even giving it a small nudge, years in advance, will allow it to change its course sufficiently that it misses Earth.
DART would spend 10 months traveling to its final destination, the moonlit asteroid Dimorphos, using autonomous SmartNav technology.
And at about 2.5 minutes out, we cease all maneuvering and we coast until we hit the asteroid.
2 weeks ago, NASA made history once again. And now the team has confirmed that the spacecraft's impact altered the Dimorphos orbit around Didymos by 32 minutes.
For the first time ever, humanity has changed the orbit of a planetary body.
You can see that at least the DART mission and proven that human beings are able to do something to deflect the incoming asteroid, that is, avoid the impact directly on the surface of the Earth. The other object we'll discuss in this chapter is comets. Comets is very beautiful due to its long hair. And comets, similar as asteroids, they are also a very small object in the solar system. Differently, that is, the comets usually have a larger percentage of icy material. Why the comets looks very beautiful is because it was able to develop an atmosphere as it approaches the sun. In terms of the how often we're able to see the comets or the period of comets. Comets usually have a very elliptical orbits around the sun. So only when the comets are very close to the sun, we're able to see it, because compared to the other part of comets orbit, Earth is very close to the sun. And there are most of comets, they are very long, what we call long period comets. They have a period over a century or two. And a few of them are actually short period comets. They have a period that range from a couple of years to 200 years. One of the such short period comets is Helios comets, which has a period of 76 years. So last time we were able to observe Helios comets is 1986. So the next time we're able to observe Helios comets will be 2016 too. However, a lot of comets are long period comets. Or like say most of the comets have very long period. It will take thousands of years to return, or if they return at all. And the short period and long period comets, they actually come from a different part of the outer solar system. We'll talk about later in this chapter. In terms of these long period comets, we actually have two visit Earth in late 1990s. The comets were called Yakutaki, actually visited Earth in 1996. This comet have the period over 10,000 years. However, although this is not our definite number, because the comet's orbit is very unstable, there is sometimes the comet's orbit will change by the gravitational influence of nearby planets, so those numbers can change. They can become even longer or shorter. And another beautiful comets, we actually already show you the picture as a cover page of this chapter, is a comet Hale-Bopp, which is visible actually from 1996 all the way to 1997. So Hale-Bopp's period we believe is about 2,500 years. So when you look at those two comets, this really is a once a lifetime opportunity for us to see those two. But don't worry, other than those long periods comets, we do have a comets, although not a big percentage, but we do have some of them have a period of just in a few years. So we can definitely take a look at them like more frequently within our lifetime. And we know the comets actually have very beautiful tails, and it can last for a very long time. And how the heart of a comet actually looks like. The heart of a comet, we call it its nucleus. If we take a close look, however, most of a ground-based observation instrument, such as a telescope, will no way to able to see the details of the heart, because the heart or the comet or its nucleus is deeply embedded inside the atmosphere of a comet. All the light we see is actually from an atmosphere of the comet, developed when they are close to the sun. And the only way to really to see the nucleus is by our spacecraft fly close to a comet and take pictures. And if you look at the bottom picture, and the picture on my right is a close-up of a comet Halley's comet. You can see it has a very large atmosphere, and its nucleus, you can see it's definitely, from the appearance, is a very rocky material. And this image is actually obtained by European Space Agent Giotto spacecraft from a distance about 1,000 kilometers away from a Helios comet. And other than that, European Space Agent Rosetta mission actually able to fly very close to a short period comet called 167P, and it was able to land a lander actually on the surface of a comet to look at the surface feature closely. And if you look at this is the image of short period comet 167P. If you look at its nucleus, it's more look like an asteroid. But due to its larger percentage of icy material, that's probably the primary differences. So that is the first time we actually have a very, very close by image of the heart or the nucleus of comet. And from the analysis and observation, we found that comets are actually composed of most of the volatile material, primarily the water ice, as well as the solid, includes both like rocky materials, silicates, and carbonaceous materials. And in this image, you can even see one leg of the lander on the comet. And if you want to know about the Rosetta mission by European Space Agency, you can definitely go to their website. They actually have a lot of latest story about the mission. This is actually considered a very big success of a human space mission, because you can imagine chasing a comet and deploy a lander on comets is very, very, very hard. And I want to share with you a video about this mission and why this mission is extremely difficult.
On November 12th at 7:35 Pacific time, a lander will land on a comet. This is one of the hardest things that has ever been done by the human species. It's extremely difficult to land on a comet. This is an absolute first for humanity. The comet is moving about 35,000 miles an hour. Unbelievably difficult terrain. There are about 58 boulders on the site where it lands. There are jets shooting out of a comet. Very difficult situation. We kind of describe the situation as the lander being a cherry on the top of the cake.
We've been waiting for this for more than 10 years, 20 years, and it's hard to really even think that it's really going to happen.
A very interesting story from a Rosetta mission, and it's a lander called Philae. Is a Rosetta mission was originally targeted at the comet, however, due to the delay of its launch already out of the range of the mission. So therefore, they actually decide to change their target to our short period comet 167P. And an interesting story about the lander of the Rosetta mission, which is Philae, is that Philae was deployed to land on the surface, but it does not go as smooth as planned. As I read from the story and watch the video, that Philae does not really successfully anchor itself on the surface. So instead of stay on one place, after landing, the Philae start to kind of roll and make turns on the surface of the comets. And fortunately, Philae was able to take a lot of picture of the surface and do some analysis. But unfortunately, Philae was roll in a hidden region, all the way to a hidden region on the surface of a comet. Then its solar panel was not able to facing the sun. So the lander Philae finally lost its connection with the Earth and the Rosetta spacecraft. It is also indicate it's very hard to land a lander on a surface of a comet. Remember, unlike the big planets, the small object like asteroids and comets, so their gravity is so weak that it is very hard to keep the object on the surface as well. In addition, you can see their shape is very irregular and make land on the comet really difficult task. Now let's take a look at how the comet actually able to develop its long hair and a beautiful hair when it's approaching from the sun. Remember, what happens is that the comet, all this volatile material, or like water ice or other type of ice material, as the comet follows orbit and closer to the sun, you can imagine the temperature actually rise. As a result, within the high temperature, all the material we believe is a subliments. So that is changed directly from a solid to a gas status. So therefore, and it's developed the big, a thick atmosphere around the nucleus of the comets. We usually call it coma, and its size is much larger than its nucleus. If you look at the tail of comet, is always point away from the sun. We believe that is due to the radiation or the solar wind from the sun that's actually kind of driven the tails away from the sun. The tail of comets are primarily from evaporating water, and as water evaporates, it will also release some dust that was used to be mixed with in the ice. So if you look at the comet, other than the atmosphere, the coma, it also has what we call the dust tail. That is basically dust released by evaporating of water ice. If you look at this image, give you a little bit breakdown of comet structure. You can see the dust tail usually is not straight. Instead, it's brighter, but it's a curve. And other than the dust tail, you can of course have the gas tail or a smaller ion tail. We think the ion tail carried outwards by the stream of ions usually emitted by the sun. And ion tail usually is much faint than the dust tail. And the major tail actually is the atmosphere stream that away from the sun. This actually form a very long tail. And you can see there is a couple of images show that comets actually have two tails. The first one is definitely the very beautiful one is actually the image from Hale-Bopp. You can see it's a bright dust tail and the more straight but a little bit faint gas tail. And here is another example. How about if we have a very close by image, for example, those series of images from mission Rosetta we just mentioned previously. You can see as the comet get closer to the sun, there is some specific point. You can see the large jet of gas is ejected from the surface, and it's getting closer and closer. There's a lot of sites we're able to eject the gas from the surface. When we observe from a distance, that is basically the atmosphere of the comet. And you can see that the reason why the comets have a large tail, if you think about the planet or the moons have thick atmospheres, just such as Venus, Earth, or Titan, due to their large gravity, they are able to keep its atmosphere around. However, for the comet, its gravity is so low it cannot hold back this gas or dust. So therefore, when the ice melts and the dust and the gas will basically flow away into the space at about 1 kilometer per second to form this very long and beautiful tails. You can also imagine that as the comets make several journeys into the solar system, it will definitely lose a lot of the material, right? Because it's all kind of become gas and the dust fly away in the space. Where the comets come from? And we know asteroids are primarily come from the asteroid belt between Mars and Jupiter. And we believe comets, similar as most of the asteroids, are primitive bodies from early stage of the solar system. And the long period comets are from the outer clouds. And shorter period comets come from the Kuiper belt. Let me go ahead to use a picture to show where's Kuiper belt and how large or where it is outer clouds. So you can see this is basically show you the inner solar system, Saturn, Jupiter, and you probably cannot really see the orbit of inner planets. Kuiper belt is actually beyond the orbiter of Neptune. And it's roughly like 13 to 15 astronomical units away from the sun. However, if you compare the Kuiper belt to the range of outer clouds, Kuiper belt is very small compared to the region of outer clouds. Outer clouds is even outside Kuiper belt. You can see Kuiper belt is actually like a disc shape, the belt around the outer solar system. But the outer cloud instead is a spherical kind of bubble just outside the outer solar system. So you can, and outer clouds have a range from 20,000 to 100,000 astronomical units. So you can see outer clouds is actually at a very, very large range. We actually estimate that the outer cloud contain more than trillions of comets. Most of those comets, either in Kuiper belt or outer cloud, well, what we call spend nearly their entire existence. So that means most of them won't go into the inner solar system and orbiting kind of around the sun in a very elliptical orbit. So they just stay where it used to be. And interestingly, then, other than the comets come from the Kuiper belt and the outer cloud, in 2017 and 2019, astronomers actually discovered there were two what we call interstellar comets. Those comets and their orbits indicate that they actually come from outside of the solar system. And what happened to the comets and why occasionally some of them are actually able to travel all the way from outer solar system like through a very elliptical orbit and get close to the inner solar system. It suggests that are actually due to their extreme location in the solar system. They orbit around the sun, what they call near the edge of the influence of gravity. So therefore, its orbit sometimes is like loosely attracted by the solar gravity. And the orbit could be disturbed by the nearby stars, so eventually bring them closer to the sun where we can see them. So those comets, again, similarly as asteroids, some of them orbit is not very stable. And also, you can imagine where most of the comets come from because they are so far away from the sun. Their temperature is near zero, so that is the reason why the comets can preserve a lot of icy material inside its heart or nucleus. Why is it important for us to study the comets? Since we talk about comets are primitive bodies, and now we know that the long period and short period comets from different places, and the comets from outer clouds could actually help us sample the material that form very far away from the sun. And we think about that might be the debris in the initial formation of the solar system. And the comets from Kuiper belt may be the sample material that was what we call the planetesimal in the solar system, but none of this material actually later on become a part of planets. Therefore, by studying the long period and short period comets, we actually will get a little bit clue of what happens, how the materials look like at the early stage of solar system formation. Let's look at what's going to be the fate of most of comets. You can see that when the comets get closer to the sun, as its material, like the icy material, evaporates and leaves the comets, as well as some dust, and usually mixed with those icy material will also form a dust tail leave the comets. You can imagine every time the comets orbiting around the inner solar system, it will lose a lot of its material. So typically, the comets only will survive no more than a few thousand perihelion passage. That means they will only survive a few thousand orbiting around the sun, get very close to the sun, before it's losing all its like gas or dust, all this volatile material that can easily to evaporate. So you can definitely imagine every time the comets returns, it will have less amount of material. And we believe that is will be probably the fate of comet Halley in long run. So after several thousand passage close to the sun, it will be run out of all its material. And as comets actually get closer to the sun into the inner solar system, there are some, like most likely, sometimes the comets will get closer to our big planets. Once the comets that come within the gravitational influence of the planets, there can be three possibilities to the fate of comets. One, it will get too close to the planet, so it will capture by the planet's gravity, and therefore will impact with the planets. We'll see some examples later. Or second, it will get very close, but not too close, so it will be speed up and ejected, actually leaving the solar system forever. And a third it will be perturbed into an orbit, therefore with a shorter period, although the comet still existed in the third condition. That is why we talk about usually comet's period. It's not our defined number, as speed is orbital period influenced by the gravity of the large planets. Compared to the gradually mass loss, there are some comets die spectacularly. And for example, one of the example is we'll call the Shoemaker-Levy 9. This comets actually break into 20 pieces, then collide with Jupiter. And this is actually a picture showing that the Shoemaker-Levy 9 comets debris is actually approaching Jupiter and collide with Jupiter. So you can see those two images. This is a ground-based telescope image of a comet, and this is a close-by image of a more crystal clear image from a Hubble Space Telescope. You can see this comet, we call it comet linear. It's already been broken into small pieces. So you can see that is basically the end of this comet. Again, if you want to know more about the outer clouds, which is most of the long period comets come from, you can definitely visit NASA website to read more details. And I want to share with you a video about the comet Shoemaker-Levy 9 actually colliding with Jupiter.
At the close of the last century, a comet captured into orbit around a planet traveled too close and was shredded by its gravity into multiple pieces, some as large as half a mile or 1 kilometer long. Those fragments would plunge into the planet's atmosphere in a series of impacts. Would the impacts be spectacular, or would the comet fragments disappear without a trace? In July 1994, astronomers around the world watched with bated breath as the fragments of comet Shoemaker-Levy 9 slammed into the planet Jupiter. Dr. Kelly Fast was one of the impact's observers and is now manager of NASA's Near-Earth Object Observations program.
It was just incredible to watch. Such an impact event had never before been witnessed, let alone studied. Ground-based telescopes around the world and spacecraft like NASA's Hubble Space Telescope and even the Galileo orbiter en route to Jupiter were used to observe the impacts. The discovery of the comet by Carolyn and Gene Shoemaker and David Levy gave us about a year to plan our observations.
The impacts proved to be impressive. The fragments, some 21 in all, plunged into Jupiter's atmosphere over the course of 6 days. At impact, they were traveling at a speed of about 37 miles per second, or 60 kilometers per second, heating the atmosphere to at least 53,000 degrees Fahrenheit, or 30,000 degrees Celsius. Like the splash from throwing a rock into a pond, the impacts created giant plumes of material from Jupiter's lower atmosphere, which rose as high as 1,900 miles, or 3,000 kilometers above the cloud tops into the stratosphere. In the aftermath, the plume splashback scarred Jupiter's atmosphere with dark clouds of impact debris, which could be seen for months as they were gradually dispersed by Jupiter's winds.
We are still able to see changes in Jupiter's atmosphere that resulted from the impacts.
Comet Shoemaker-Levy 9 showed us that large impacts still happen in the solar system and were a factor in NASA developing programs to address the impact risk to Earth.
How you feel after watching this video? I feel lucky that the comet Shoemaker-Levy 9 actually climbed on Jupiter, not the Earth, right? That is all what I want to talk about chapter 13. The comets and asteroid. First of all, we talk about asteroid, how they looks like, and what are the types of the majority of asteroid. And then we talk about the asteroid and the planetary defense. Then how we're actually able to protect the Earth from a future impact. And finally, we talk about the comets and what comets made from and where it's originated and what is the fate of the comet.